Okay, we're going to discuss unit vectors. This is going to be section 1.9, which is unit vectors. We've been dealing with vectors in the xy plane. So things are pointing in this direction. So add two vectors together. We place the head of the one and tip of the other. We then draw a line from one to the other, and that gives us a vector, a resultant vector. But what happens if maybe we don't have vectors going like this or this? We've got them going like that. It has a whole third dimension, which means we really need to talk about the x, y, and z axis. If we have a y-axis and x-axis, we know that the positive x is in this direction, the positive y is in that direction, negative y, negative x. If we align our right hand, another right hand rule, if we align our thumb with the x direct, positive x, and our index finger with the positive y, it turns out that your middle finger bends in the direction of the positive z. So positive z comes out of the paper. Negative z goes into the paper. So we also deal with, so this would be positive z, and we draw a dotted line out the back here for negative z. Makes sense? Got it all familiar? Right hand rule. Good. Little physics gang sign. We remember that the resultant vector equals the square root of rx squared plus ry squared. Well, in 3 dimensions, it's not that different. We just use rz squared to determine the resultant vector of a vector in 3 dimensions. Now, there's also a little helpful piece that we can use, which are called unit vectors. Now, a unit vector extends 1 unit in each direction. So 1 unit in the x direction is called the I hat vector. 1 unit in the y direction, heck, let's do them in red. See if that helps. 1 unit in the y direction is called the j hat vector, and 1 unit in the z direction is called the k hat vector. So if we have vector A, for instance, we have a y component that we call a y j hat. We also have an x component we call a x I hat. And so we can describe vector A as a x I hat plus a y j hat. So I and j just represent a unit of 1 in the x direction or the y direction of j. Now let's imagine we've got 2 vectors we want to add together. Let's say we call it vector B. So vector B has its components. That would be B, Y, J hat, and this one would be B, X, I hat. So we can describe vector B as bx I hat plus B, Y, J hat. So far, so good. We're just describing each vector in terms of its components and its unit vector. So, let's say we want to add the two together. So we want to add A, vector A, plus vector B. So it makes sense to say that vector A, since it equals AXI hat plus AYJ hat, we can write that here. AXI hat plus AYJ hat. And then vector B, if that equals BXI hat and BYJ hat, we can write that out as BXI hat plus BYJ hat. Now this may seem kind of cumbersome, but this is where the magic happens. This is where the algebra kind of takes over. Because, you see, if we rearrange these terms, we can write it like this. AXI hat plus BXI hat plus AYJ hat plus BYJ hat. Now, see, you got J's in here and I's in here. Well, we can just take those out. So we can have AX plus BX I hat plus AY plus BYJ hat. Now, you might remember that Rx plus Ry equals R. And Rx equals Ax plus Bx. And Ry equals Ay plus By. Well, hey, look what we got here. Ax plus Bx, that's Rx. Ay plus By, that's Ry. So, the resultant vector, which is A plus B, is going to equal Rx I hat plus Ry J hat. And if we want to take it to 3 dimensions, we can say that R equals Rx I hat plus Ry J hat plus RZ K hat. Nice little formula that you're going to need in a little bit. So let's do an example. Skip another piece of paper here. Let's imagine that you've got 2 vectors. Vector D and its components are 6I hat plus 3J hat plus, minus 1K hat. And you've got vector E. That equals 4I hat minus 5J hat plus 8K hat. We want to find what vector F is. And vector F equals 2D minus vector E. So, if D equals 6I plus 3J hat minus 1K hat, we've got to multiply this by 2 and then subtract vector E. Well, we can just substitute in. 2 times 6i hat plus 3j hat minus 1k hat minus vector e, which we can just copy down here. 4i hat minus 5j hat plus 8k hat. Now we multiply by 2, so we're going to get 12i hat plus 6j hat minus 2k hat minus 4i hat plus 5j hat minus 8k hat. Now we've got one long expression here that's got some like terms we can combine. So 12i minus 4i equals 8i hat. 6j hat plus 5j hat equals 11j hat. And 2k hat minus 8k hat equals 10k hat. So now what we have is we've got each of the components of vector f. And if we go back to our little formula here, the resultant vector equals the square root of rx squared plus ry squared plus rz squared. We can just square all of these components to get the resultant vector f. So that's going to be 8 squared plus 11 squared plus negative 10 squared. So you've got to square the component before you add them all up. So that's why the minus sign's inside the parentheses. It's not a subtraction here. I made that mistake earlier and got a completely wrong answer. Anyway, if you calculate all this out, the answer becomes 16.9. So that's how we use unit vectors to determine magnitudes of vector equations. So you'll get a chance to try that later.